I circle around?
Sure. Okay.
And the lecture that follows this will, again, by a funny approach to symmetry analysis in quantum mechanics, where we sort of look at it from a eagle's eye view, where you see sort of all the things going on at once. And we'll just start with the simplest symmetry, the symmetry of the cyclics, the waves that go around rings. We're going to have a little bit of that today as well, because I really want to make a point about the weird dynamics that occurs in quantum mechanics. And I'd like to, as you see at the bottom of this, some of you have already seen this, quantum dynamics of infinite square well and Bohr rotor. That I want to show and spend some time with it and play with it a little bit using the animations that we have available. And the difference between having a Fourier spectrum that's, shall I say, a civilized Fourier spectrum would be one that has a Gaussian profile. The uncivilized one is sort of the opposite, where the profile is what they call a boxcar. If you're an experimentalist, a boxcar spectrum, you've probably heard of that. It goes up to a certain point and drops suddenly. So you have constant Fourier value, and at some frequency it drops on either side to zero. It's very uncivilized, and we'll see that the dynamics that results from that is also uncivilized, but also beautiful. There's some beauty here, even in the uncivilized cases. In any case, the last time that we met, we just sketched out the frequency hierarchy, which is shown as a sketch here, and then a real example of it involving a molecule Freon out of the handbook, so-called handbook of 2005, is in the slide at the third screen here, and the P, Q, and R branch of it in section B, the second section there, is something I want to show also before we get into the wave dynamics. These are all things that I'm going to be spending a lot more time on later on in this course. So let's go ahead and just look here again at things. There's the PQ and R branch circa 1996, actual pen and ink drawing being taken out of a PHYS A article, which is one of the articles. The CF4 article is one of the ones that we have listed in our giant dictionary of papers that are relevant for this course here. So, and then this is the monster, and then the super monster that the C60 will produce is where we're headed. I'd like to actually be able to, maybe by the end of this course, calculate some of the constants you need to predict the spectrum for experimental work. And we've talked about this as far as the amazing power of the symmetry, that is the Fermi versus Bose symmetry, is really shown here more than anything I know of in physics. And we talked about ways to understand frequency, and reminded you that molecular physics for a long time really only served the astronomy community, particularly the radio astronomy community. Now, the models that we use to handle a hierarchy, like the CF4, SF6, or hopefully C60 hierarchy, the models that are used there and for any molecule that gives a spectrum has energy levels that, first of all, start off just being atomic orbitals that hold the molecule together. Bonding orbitals, non-bonding orbitals. We're going to be maybe touching a little bit on that, but that is involving the very highest frequency that molecules can exhibit, and that's when you get the electrons vibrating. They're so light that their frequencies are visible and above easily. And then the next stop is the vibrations, and the vibrations are mostly in the infrared. And the vibrational transitions, of course, you can have transitions that go over many bands, and that can be, well, anything, just like the electronic spectra. And of course, that's very interesting to modern research, where we're trying to figure out how these molecules behave when they're washed in a very strong laser light. In any case, this spectrum here goes mostly as the inverse square of the quantum number, principal quantum number. This spectrum right here is just first power in the principal quantum number of a harmonic oscillator. All of the splittings here for a harmonic oscillator, harmonic means every single difference is the same. That is, every single transition that occurs between neighboring levels is the same, and between two levels is twice that and the same everywhere. So that's the very first model, and it's the only model really that we as humans can analytically solve for a really arbitrary number of dimensions. And that is the thing that's happening with a molecule, is that there are many degrees of vibrational freedom in a polyatomic molecule. The C60 here has, now I've got to think again, 175, right? It's 3 degrees of freedom times 60 is 180, subtract 6, right? Subtract 3 translations and 3 rotational degrees of freedom. So 180 minus 6, that's 174 degrees of freedom. That's 174 vibrational modes, fundamental vibrational modes. That's without stacking up 2 or 3 phonons. They don't use the word phonon for this, but they should, because it's a lattice. And the complication of having a spectrum with all of that activity is what has really retarded and made it impossible to look at this molecule so far. So we're going to have to cool this baby. Yeah.
Can you put this update this? It's because
Sure.
it's difficult for me to see it.
Let's go back on this one to this point right here, just before that. And there we are. Okay, is that
Much
better?
better. Yeah.
I actually had Dick come. He was going to switch to projectors, so he put this one down on number 3, where we don't really care if it's a little dim. But he had some problems, and you can see by looking at the hardware up there that it's not trivial to move those things. So next time maybe we'll have them in the place where this is bright, as is that one. Okay, and then the next thing I want to point out here is that a lot of the sort of free motion spectroscopy involves levels that go quadratically with the, well, in this case, angular momentum, with action, if you will. And so you have a spectra with quantum numbers which are getting squared multiplied by some constant. So this is just either a Bohr mass on a ring, or the other one that has a quadratic spectrum is just a square well. This is two-well tunneling, which is a whole other subject. I want to deal with both of those sort of dynamics in detail today, just to see what the models do. Okay, so the basic theory that you're using as stated there. Harmonic oscillator, linear spectrum. Rotor, quadratic spectrum. And then complicated when you put two of these next to each other and let some tunneling happen. And that's what's a big part of the fine structure of these molecules that occurs. And we should also point out the thing that we're going to review is how closely connected the two-dimensional harmonic oscillator is to the rotors in 3 dimensions. So that's a real saving grace. That's something that makes turns our theory from a pain in the butt to something that's really beautiful. So I don't want to de-emphasize that at all. So that's the thing that we will deal with. Now here we're just dealing with really one dimension, but it is something that moves in 2 dimensions. So it has some properties of something that actually takes up space. These other guys here, this one right here really is one-dimensional. I call it the infinite square well prison, and I'll say more about that in a minute. But the basic idea that I want to make clear is that these two, as far as what goes on in the little spaces between the ends of the diagrams there, are the same. The infinite square well, and I put it up here too so I can point at it in front of the screen. The infinite square well, right here, has the same wiggles as you see over here. Okay, they're basically what's happened here is I've taken 2 of these, took out this area here, and tied the ends together so that I can make a Bohr rotor like this. Okay. Now the Bohr rotor gets to do a lot, well, twice as much plus 1 that this thing can do. And I think that's something that you just should keep in mind, particularly if you're doing solid-state physics and you're making a one-dimensional lattice and you decide you'd like to do something in 2 dimensions. The changing of the topology of this is really very beautiful and helpful. It's a very simple example of that. So here we have the infinite square well. The empty space here, W, is the same as the half of the space that's over here. But this one only has sine standing waves because the boundary conditions force us to have 0 values of the function, but not necessarily 0 values of the derivative at the ends. And in fact, all of them have non-zero. All the eigenfunctions have non-zero values at the edges of this. But that connects very nicely in this case because it gets to go all the way around. So the square well with its same standing waves graduates to become sine and cosine standing, or any linear combination of the sine and the cosine, including what we call moving waves. That is, cosine plus I sine is a moving wave. So you can have a wave that has, if you take its magnitude, a constant value all the way around, but the phase inside it is moving either this way or either clockwise or counterclockwise. Counterclock, and this is clockwise. Left hand is a negative motion by convention. Now the other thing that's different about these two is this one has a 0-point energy, but no level at the floor of the prism. Okay? This one you have a state that lives on the floor at 0. Okay? So you get one more state that this one can't have. You don't have any n equals 0, but you do have m equals 0. And m means number of nodes of the wave is 0. And that wave would be right there. That's got a constant amplitude. So that's something to keep in mind. Uncertainty principle, which we're going to mention just in a minute here in some funny way, is responsible for that. So this one has a 0-point energy. In other words, your first state has to be a certain height. we'll write that down in a minute here. And the other thing is every single one of these levels for the Bohr rotor are doubly degenerate. Only this one is singly degenerate. So if you're going to be teaching quantum mechanics at some point when you get out of this place, these are little things to mention. These are little things to remember that are important, very important. Lets you have a better picture of what's going on here. So in addition to the sine waves, we've got cosine waves that are, well, orthogonal to the sine waves. That's all I really have to say about the topology of this. Let me get this one lined up here where I point out that business about the complex wave. So let's look at the prism here. And what I'm going to do here is just go real quickly through this. And I'm going to do the same thing on this here. Okay, just write down what are the solutions. The solutions are sine waves with a certain amplitude, which we can mess around with to get what we call orthonormalization. We won't play that game too hard here, but basically we're going to have, here's Dirac notation for that sine wave. The energy with a state of position as a scalar product, and we've got the squared quantum number giving the heights of these levels here. And let's go ahead and just keep these things going here. We have the 0 point energy right there. We have the first transition, which I'd like to look at real quickly here on the animations. The first transition is the beat energy between these two, but let's just talk about the states whose absolute values do not move. The ways this system can play dead. That's what eigenfunctions are. They're the ways that the waves can play dead. Nothing moving. That is, nothing that you can see moving, because you can only see the psi star psi or the magnitude of the wave function. So there's 3 ways that this system can play dead. And most of the time we think of it as being in the ground state, dead. Okay? And the 0 point energy here is, well, what we've got is that's our parameter, and then 3 times that is this first beat energy here, and then 5 times that is right here. So things going up quadratically. Okay, so that's just sort of the topology that we're talking about here. Now, what we're going to do eventually here, and let me also point out on this that the constant here, the kind that we're interested in as a molecular model, we're interested in the inertia of the molecule, the inertia constant for the molecule. So this little parameter right here, if you're using MKS units, is called B. Almost always the B constant in a molecular, as a molecular constant, is the inverse of the rotor inertia. And that's just because the Hamiltonian is P squared over 2 times the inertia. So in a molecular physics, the J squared times B is the very first term in the kinetic energy of Hamiltonian describing any molecule. Now that B, you say it's constant. Well, not necessarily as you go to higher states. The molecule may swell up a little bit as you go to higher states. It's very seldom that as you go up higher energy it contracts. So we don't increase B, but we do reduce B by exciting most molecules. Anyway, that's not an issue here. Here it really is a constant. We're stuck in this prison. And if it's a Bohr rotor, we're stuck on this ring. And we're making energy levels that are just exactly these energy levels plus the bottom here if you've got a rotor. So that's where we're talking about. So today we're going to look at the real dynamics, first of this thing. And this is in the textbook in Unit 4, Chapter 12. And I recommend you read that chapter because you'll learn some things about the square well, some of which we'll talk about today, but almost all of what we'll talk about today is just not anywhere else. So you get a chance to see some funny dynamics that really this one does a much better job of, so we'll spend only a little bit of time on this. Anyway, the chapter 12 is written like a bad novel. It's the story of somebody in prison. This is called Prisoner M, M for mass. So we have a mass that's been put in a prison with infinite walls. And I must hope that nobody here is going to do something so bad that they get put in a prison with infinite walls. But that's what's happened to Prisoner M here. Okay? So the story is about the physiology of Prisoner M that has to live in a hostile situation like this. Okay.
Well, what was the crime?
Well, as I said, I hope none of you do something so bad as to be put in this. And I would not hope that for anybody. I do think of one exception, though. And I guess you know who that is. Okay. So
you say something about golf tournaments.
Right. Driving your golf cart on the green, you should be put in this prison. Okay. Anyway, let's go ahead here, because it is the Bohr rotor that we will eventually want to look at. But before we get there, I would like to look at just the geometry of the profile spectrum that you see on the third slide down there, namely part B of the CF4 spectrum. Has a, in the case of that spectrum down there, the P branch is on the left, the R branch is on the right, and the Q peak, which is also a branch, but they're all piled up on top of each other, is in the middle. And this is an actual spectral trace of an experiment involving the infrared band of CO2. And we've got a B value here, 0.2 inverse centimeters. That means a lambda of 5 centimeters and a frequency of 60 megahertz. Okay, so that's a typical frequency for something going on with the CO2. Okay, but of course it's got lots of transitions, lots of spectra. Okay, and the temperature determines this profile. Boltzmann law determines this profile. But this down here is a diagram that, and I'll back up so I'm pointing at this part of the thing. This is a diagram that lets you convert energy levels of the initial states and energy levels of the final states into the actual spectrum, which is just a plot of the differences between these guys and these guys, subject to a constraint that we will call the dipole rule later on, but that's the dipole rule saying that the angular momentum can only change by 1 unit.
Here, what are the initial and final states?
All of what I'm putting right here, these are this is the molecule as it came into the lab in the morning.
Okay.
Unexcited, it had all of these states.
Okay, so before you shine light on the molecule.
And then you shine the light, the laser, okay? And each one of these can jump by 1, either up or down, okay? Those are the two possibilities. So, for instance, this one, if it was in J = 3 when it started, and it jumped, I'm sorry, this is J = 3 right here. If it jumped down to J = 2, that's the point it would be. So that's a P point. Okay, P for plunge or plummet. Okay, that's the way I remember it anyway. All right. If for some reason, and this actually is possible with certain molecules, not CO2, but in some cases, it could take the light in and stay the same J. If that happens, then it's called staying status quo.
So what happens to light? Because if it absorbs light, then it will, it has to.
It's a Raman process. That would be the easiest answer to that. Okay. It puts it in and then the light that comes back out again.
Right.
There's a little bit less energy as a result of this thing jumping up. And then finally, if you were to go up 2 steps, or you started, say, in 3, and let's see if I've got this right here. If you just let this thing emit and reduce, let's see, no, I've got it backwards here. This is J equals 3 going, first of all, to J equals 2, that's a reduction. Here's staying the same, and here's raising it. If that light takes J equals 3 up to J equals 4, then that's the one that we'd be drawing a 45-degree line right up to there. So that is the R3 line right there. You see the rule is whatever angular momentum you started with is the number that goes into each one of these. Q3 is in there somewhere, but P3 is over here, you see. So this is a nice roadmap that leads to the actual spectrum. And believe it or not, when I first wrote this Reviews of Modern Physics article in the 70s, no one had done this. Now that people do Raman spectroscopy, you start seeing people talking about two-dimensional spectroscopy. That's a drawing that's very much part of our lore right now. Yeah?
You mentioned delta J at 2. About how is that for?
Well, most of the time, if you were to do a raise, say you were at J equal 4 right here, and you were going to go to J equal 5, that would be a raise. I'm sorry. That would be a raise of J.
I was thinking of quadrupole transitions. You pointed to it before.
Or a full Raman, right? You can have then much more complicated spectrum from a Raman, because you could jump, if you jump, allowed to jump by 2, okay, in a normal transition. Okay. Now there's a catch here. B, the constant, here is assumed to be the same initially and finally. Actually, it's a little bit bigger, and you can see that by looking at this one, that the actual motion is very, very small, but it has moved a little bit. Okay. So if you take this thing right here and scrunch it down by making the molecule heavier, okay, you're going to get these things peeling off of the Q branch to make a mess of lines. Okay. Now here's something else that I want to make a point about, because we're going to be using this in a lecture ahead, a couple of steps ahead of right now.
Dr. Hart?
Must use.
Dr. Harter,
yes.
So here you have just considered the rotational degrees of freedom, right? In this example. So you have ignored the vibrational degrees of freedom completely in this example, right?
That's what I'm doing here, but this diagram would still work
Okay.
if you came in with a ground state vibration,
Okay.
and then way up here, right, you've got a set of rotational levels for it, right? Well, you take that piece of paper and bring it back down, and then you get a spectrum like this,
Okay.
you see, in which you have increased by 1 vibrational quanta, and then all of these rotational quanta made the changes that we just
So you could
discussed.
still get an identical graph.
The same graph works, because all this thing is doing, taking the difference, right? Doing a 45 is just taking the difference. Yeah, in this case by 1. Right? J is changing, but just by 1, or not at all for that guy. Does that answer what you were after? Okay, but notice you would not get this if you were to let your Hamiltonian simply be J squared. See, what we've got here is J times J plus 1. We've got to make a big fuss about this, because this is the thing that's going to give us a really cool way to calculate fine structure are to show fine structure. It's kind of neat. But in any case, what I've got here is 0, 2, 6, 12, 20. If I take half of that, that's 1, 3, 6, 10. You should recognize those as triangular numbers, right? So it's quadratic, but it's this weird kind of quadratic. Here I'm just putting a good old 1, 4, 9, 16. That doesn't work. It's got a big gap here. So this is proof that quantum mechanics of angular momentum that gives you j times j plus 1 as the eigenvalue of j squared operator is got to be. Okay? We have more complicated arguments, which you've probably already had for that result. But I want to make very clear that this right away shows us that that has to be. Okay, anything else? Rotor energy Bj squared. No way. Not when j is just an integer. Okay, let's go ahead here now. Should have left it over there. All clear?
Yeah.
Okay, so far. Okay, now the quantum dynamics of these guys. That is, I think, an important piece of our story here. Now, what I'm saying here is, you know, what is it? How and what makes a dipole spectrum? What was really going on in that thing? What gave us the light? All right, how did it? And the real answer is you've got to get the thing in a state that isn't dead. As I said, this is dead, because it, you know, this absolute square of this thing does not move. The green lines there are constant. The envelope of this wave function and this wave function is constant. And this is a quantized wave because it has a definite number of half wavelengths in this infinite prism. What you need to do is a half and half, or something like that. It could be a third and 2/3, it could be a tenth and 9/10. You've got to have a little bit of one other state in this beside. Now here it's half and half. I'm just putting these two waves right on top of each other, adding them. Okay, half and half. I should put a half and half on this. Actually, I put 1 over the square root 2 on that in order to make it normalized, but we're not arguing about amplitudes that much right now. But in any case, this is what I call exercise in prison in this particular figure in chapter 12, 12.1, subsection 1. Okay, infinite square well eigensolutions slashing back and forth, and that's what I really want you to get a feeling for what that means. The motion of quantum mechanics comes from having at least two quantum states summed up. Some amount of two. It doesn't have to be half and half. That's what we would call a saturated transition when you get half and half. Okay, so let's play with some of the animations that come with this. And to do that, I'm going to switch over to this thing right here. And this is a very interesting one, which I'll, for the moment, hold up. And that is, I'll see if I can get the right, I got to get the right computer here. Let me go ahead and just pause this one for a moment and go over on the other screen and get that one going. This one right here, which involves just a single well with a quantized state. Now this isn't quite an infinite prism. This one has got a very finite set of walls, and it's a weird sort of programming that I've done to make all of these things. I'm really only using 24 oscillators to fake a prism here by making their spring constants really pretty high and then reducing it down to 0 for the ones in the middle here, and then bringing it back up again.
Now, why
there.
is it? Why'd you make it curved like that? Is that some sort of Fourier
Well,
series?
if I'm only going to use a 24, and we can put more on this so that it becomes square. If I'm only going to use 24, then when I describe the thing, I have to use points that are on one of the 24 sets there. You see, so I'm setting the frequency of their motion with those little dots. And that's equivalent to making a potential well for the wave that's made out of all of these pieces here. And this is an interesting program of which we do not yet have on the web. The basic idea is I can make all kinds of waves for this thing. I won't do it right now. I'll zero that out of here right off the bat. But what I will do is show the ground state. So there it is. It's dead. Now its heartbeat is still working. It's still beating its heart, but the body is not moving at all. The envelope of this thing is not moving. The magnitude of this wave, real and imaginary parts, they are going back and forth. The dark blue is the real part. The light blue is the imaginary part. And they're chasing each other. And you can see the phasors down below there that actually describe the complex numbers at each point that's inside and a little bit outside the well. We get an actual evanescent wave as a result of doing this. And that's what you get for not being an infinite prism. You get a little bit of evanescence that gives you a chance to escape if you wait long enough and let this run long enough. But this is a really sneaky way to make wave dynamics. Now the next wave that this thing has the next quantized wave, the next way to play dead is this one right here.
One note.
And it's a little faster, a little bit higher energy, okay? But there, once again, the envelope of it does not move, okay? But what if I add, say, half and half, that is, make the equal amounts of these two waves? It sloshes. And that's what we're talking about right here. Excuse me. Or right here. Okay? That's the sloshing that we're talking about.
So, Dr. Harter, in the earlier case, when you had a perfect standing wave, the parts which moved were the real and imaginary parts of psi, right? The wave function, right?
That's correct. They each have their own quantized frequency. Let's go back and do it again. I'll zero this one. Oh, this is kill it. There's nothing in there now. Okay? And I turn this one on.
Ground. No nodes.
And that's a symmetric wave. Let's get some symmetry language here. That's a symmetric wave around the center of the well. Okay? And the next one is an anti-symmetric wave around the center of the well. But both of them behave like this in the time domain, and that is their hearts beat, and whatever their quantized frequency is, that's their energy, okay? And you can see that this particular one has an energy that's about that much right there. So it's just a little bit above the floor of this well here. That's the 0-point motion right there, which this wave has. 0-point energy. But it has no motion as far as anything that you can see as an ordinary mortal. That an envelope wave right there, the skin of the wave is absolutely frozen. That's what an eigenstate is. Dead.
That's right.
Okay?
But Bill, I'm still wondering about the bumpy surface of the bottom of the well. Why is the potential
That would
bumpy?
go away if if you wouldn't even ask the question if I had used some of our modern stuff where we can put 1,000 dots, then it goes and straight as an arrow.
But what are the dots supposed to be?
Well, this is the Fourier transform of a discrete square well. That's what
With
that's
no more
what you're
than
seeing is the
24
wiggle,
terms.
and they're not really wiggling. There's the line. I just drew the line in there. If I didn't draw the line in there, you wouldn't ask the question either. You see, this is a sneaky part of this animation is that this is a cool way to make waves discretely, so to speak.
So the eigenstate is that.
That's the
which
Gibbs
isn't-
phenomena. The Gibbs phenomena. You know, the little thing when you
Yeah.
use a
Yes.
trigonometric series to make a square, try to make a square, it will never get you.
So then
Good derivative.
this eigenstate that you've depicted, it's got a continuous curve.
Oh,
to it.
it's really immune to any of the sort of wiggles that are down there. It's just reading off of the points that are sitting right on the bottom red line.
But is it, you know, when I look at the animation, I can't necessarily see the equations right away. Is that continuous curve calculated from the continuous curve of the potential?
It just fell where it may. There's nothing in here except an equation that's connecting these oscillators and having their frequencies vary as shown by those dots. So it just comes out. Now if you look really closely at this one, you can see that it's not totally a smooth curve right there.
Are you using the Schrodinger equation
No.
here?
No.
No.
No, this is the basis of the Schrodinger equation. You see, this is what's so cool about this is that you don't have to derive that thing. This textbook does derive it, but we derive it from relativity, which is the only honest way to do that. And then you truncate it. You throw away MC squared.
See, part of the confusion might be is we're taking even in the finite case, we're taking something with an infinite changing derivative.
Yes.
It's very difficult to approximate
Yes.
anything with a shock like that
And
with a
Fourier
continuous function.
sines and cosines can't handle it. And that's called the Gibbs phenomenon. How many people have heard of the Gibbs phenomenon?
Heard of it, but
You've heard of it?
yeah, but I don't remember it off.
Do you remember seeing in math phys Gibbs phenomena?
What?
When you take a Fourier series and start to make a square well, that is a, right? And it's basically cosine of 1 times phi, okay? And then minus a third times cosine of 3, plus a fifth times cosine of 5, minus a seventh times cosine of 7, right? If you just keep adding that series up more and more, the wave get closer and closer to a square well. But all the times you're getting this little kinky thing where it goes around the corner at one side and then does it at the bottom. It goes like this, doink, and then like that. And even if you go out 1,000 terms, it'll just go right up to about 1,000 from there and go 1,000, and you always have a constant height there called Gibbs jump. Josiah Willard Gibbs, American physicist. One of our, at the time we didn't have any physicists, right? It's like,
It's actually the worst part of the Fourier analysis is the Gibbs.
Yeah.
Probably the worst part. Worst thing I've ever seen in Fourier analysis. Other approximation methods probably don't have that problem.
yeah.
You know, maybe this question is too.
Actually, you go in with a slope like this and just jump, you're going to get it also.
Yeah.
Anytime you got something in there that's got infinite slope, Fourier can't handle it. It takes infinite frequency. But even if you use infinite frequency, it's still going to have that damn error. Gibbs error, you could call it.
So, what is the algorithm that allows you to calculate these eigenfunctions? I guess I'm still confused about that.
Oh.
It seems like there's some computer program going on here. What have we described the algorithm actually?
No, not totally. But basically what you do is you convert the, one way to do it, it's not the way I did it, but one way to do it is take Schrodinger equations and write finite difference equation for it.
Okay.
Right?
So
But there's a sneaky way to get that.
There is a Schrodinger equation.
Yeah.
So,
Not here.
They're the pieces of it.
Dr. One last question. So I'm a bit confused about what causes the real and imaginary part of psi to wiggle, to oscillate. Like what causes? What is it?
Well, suppose that I had no potential at all, then this would just be a plain wave.
Mhm.
And so the answer to your question would be, it would just be the real and imaginary part of e to the I kx
Right.
minus omega t, that of a plane wave, right? Or we put the two together so that you just get something that has a sign
That's right.
like this, right? And it's got to have a real and imaginary part. That means it's got to have a position, that's the real part. And then the imaginary part is just a derivative of that thing with respect to time divided by omega, whatever the omega, local omega is.
Mhm.
So that's the imaginary part, which is the light blue line.
What does imaginary part physically mean?
So, see, there's the real part. The real part hits the top just as the imaginary part goes through the origin.
Right.
Right.
So
So
we're
Dr.
viewing
Harter-
an eigenstate,
Dr.
but then
so
we're
I
letting the
see-
time evolve.
So I know like the real part,
Same thing.
like I
We're
know
starting
like
with an
intuitively it
eigenstate,
makes
but then we're letting
physical
the
sense
time
to me.
evolve.
But what does like actually the imaginary part means? Because I would think like, well, if I have something vibrating inside a well, I will have like,
Yeah.
there are
Right.
infinitely many reflections inside that well.
Phase, whatever you call
But
it.
what does really
That's
that,
making it too complicated. You probably,
you see what I mean, right? Like I'm finding a physical interpretation, a visual thing for
Uh-huh.
that, for me to the imaginary to make the imaginary part to make sense. Because if I have, it's like, if I have like, for example, like in the case of the barrier, when I have like a wave and it travels through it, then inside the barrier, the wave, there's a reflected wave inside that goes back
That's
and
true.
forth infinitely
That's
many
true.
times. It just
we should resume that thought.
Mhm.
Right now that thought is hurting us.
Oh,
But
okay.
later on with the thing we call bandit,
Uh-huh.
we make a big deal of waves, reflecting. Okay, that's the other way to do waves, which I think is much better for many things. But this one I want to stick with, just this one right now here. And I want to stick with real and imaginary as something that's very fundamental to oscillation.
But you see, where is my thought coming from? Trying to visualize
The way to
trying
visualize
visual-
the
physical.
imaginary part is as the derivative of the real part, divided by omega.
Yeah, but the physically, what does
Well,
that
what
mean to
about the
particle?
phase integrals? Maybe Luis is
One
asking about
question at a time.
integrals for the phase.
Well, just the phase values, which are what those clocks are doing,
Yeah.
right? Those clocks down at the bottom are trapping, the real part is up, and the imaginary part is this way. That might get a little bit of confusion here, okay? For each of these clocks, I've taken the ordinary phaser that the physicists use, the phaser that makes things go clockwise, right? This is the position, this is the velocity, okay? And the velocity, you see, is positive here. So at the top of the phaser, you have no choice but to go this way. That's the visualization I want you to get. Okay? So the phaser has to go left-handed in a physicist world, because we're used to writing X and P as our phase space. That's Poincaré, right? Henri Poincaré.
But here's another idea. Since when you talk about seeing a quantum wave, all you can really see is the static probability distribution.
As an
So-
experimentalist.
As an experimental.
But a theorist is better than an experimentalist in the sense that he can build things like this and show, right?
Theoretical supremacy.
Yes, theoretical supremacy.
But now here's the other thing. You can see the phases if you're mixing two waves together.
Absolutely, that's what we're going to do.
Everyone, the theorist and the experimentalist,
Right.
can finally see the phases
Yeah.
when the waves are mixing
With
together.
a little correction there, because you see, as soon as you go up to a quantum system with something that's going to be phase sensitive, all of them come part of the system again, right? So you aren't really looking at the phase that was there before you touched it. You're looking at a combination of your phase, your heartbeat, and its heartbeat. And that's not the same.
Well, it's as good as you can get.
It's as good as you can get experimentally. Right.
Dr. Harter, one last question just before we proceed. So I understand why the solution has to be a standing wave. That one I understand. But if I were to forget that fact, and if I just were to look at the real and imaginary parts which are oscillating,
Which are
in this case here oscillating,
Yes.
how do I then construct the standing wave from these two oscillating parts, like from the real and imaginary parts?
Square them, add, square it.
I didn't hear
You,
what
you
said.
square the real, add
Yeah.
it to the square of the imaginary, and that gives you your
More size
modulus.
squares.
Yes,
That
that's probably
still
the
would
best
be
way
an
to say
eigenstate.
it.
That wave would be an eigen.
Yeah, you're just talking about one phasor.
Envelope
That
of
we- Ideally, we'd have an infinite number of phasors to make this wave. I've only got 24 there. I'm
Oh, I get it. Yeah.
very
I get it.
cheap. I'm cheap with my phasors.
Okay. And then they all cancel and you get a standing wave.
That
Cool,
wave,
right?
Yeah.
It's cool. Yeah. Now another way to say, and this is just a joke, but it's a good joke. You know how Bell Labs got crushed by the predatory capitalists because they said that you get your research, but you got to get a result by the time we have the next stockholders meeting. Right. Right. That's 1/4. Right.
3 months.
Okay, so the way the phasor works is imaginary, precedes reality by 1/4.
Which ties back into that idea of the imaginary can be the momentum.
Yeah. See, the imagination precedes by 1/4 the reality. Okay. Now the reality here is 1/4 now behind the imagination, right?
Right.
Imagination perceives reality by 1/4. Terrible idea in business. What's responsible for all of quantum mechanics in the real world of space-time. Okay, now let's come back to this guy right here. This one pretty simple, and the mixing of the waves. And I would point out also on this one that if I get even the slightest amount of anything up here, let's just take the one that we've been taking, this one right here, if I take the slightest amount of that, it starts moving right away, a lot. See it sloshing back and forth? You can hardly see what I put in. I put 1 pixel's worth of the excited state. That's something to remember, because that's what's going on in this room. All the light that we're getting is due to, say, on a tungsten filament, okay? An excited state being excited, I mean, the jump is this big, but it's only being excited a tiny, tiny, tiny amount. And we've got so much charge. I mean, you've got 10,000 coulombs in every little, cubic centimeter, right? So it doesn't take very much to get that wobbling, and then it radiates. Now that's charge radiating there. Look at it. At the frequency that is the difference between those levels. That's the way photons are made. And the reverse is true. That's going to come down, and it's going to be very slight motion of the excited state when it gets absorbed.
So you're saying like wave packets is just a bunch of wave mixing things?
Waves are the way to go, man. They ain't no particles. Not the classical way. You gotta do it with waves. And it's sometimes very counterintuitive, but this is not so counterintuitive when you look at what we've got here. Now, what about the symmetry? And I'm making sure that our clock is okay. We're not too far gone here. But let's take a look here at what I can have as far as the waves go here. I'm going to zero this guy out again. Erase. Here is the ground state of this system. And let's resume. This one is symmetric, just like that ground state over there. It's just like, and let's kill everything and get the ground state of this thing going as well. Zero it out and start the ground state. And that's one of the theorems that I believe was Schrodinger, but maybe even some of the other guys proved, was that no matter what your potential is, your ground state has no node. This is speaking in one dimension. No matter what it is, you're going to pay for energy if you let that wave function cross the zero of an eigenfunction. Okay? So they're two symmetric waves, but this one is symmetric in the sense that if I had a really high barrier here, they would always be in phase. And it's dead. It's got two hearts now, but they're the envelope, the skin is not moving. Okay? And if it's a really high barrier, it's an almost infinite prison, it isn't going to make much difference if I mess around with it like I was messing around over there. But let's real quick take a look at the other state that is present here. I'm going to kill the ground state, and I'm going to look at the so-called excited state. It's not very much excited, as you can see by the energy spacing there. But here it is. And it is anti-symmetric. Let's kill this one and make this one have a time going for it. Okay, so that one's anti-symmetric, so is this one. Not too different because I don't have a really big barrier. Okay, but if I had a really big barrier here, this thing would come right up to it and have very little wave inside there, and then something that copy it with a minus sign on the other side. While I'm at this, I'm going to advance so you can see the two things on this static drawing here that we're talking about. Okay? Now, let me point out on this one, again, that the energy between these two, right here, is really small. It's less than a pixel, so you can't see it. There's a tiny splitting between these two levels. That's like those tunneling splittings that are in the superfine structure that we're going to be talking about for the molecules. Much more complicated problem involving angular momentum tunneling, okay? Here it's just a plain old sophomore physics wave tunneling. But there's a very small splitting there, and I didn't have time before class. I could blow this thing up so you could actually see the pixel between these two. But we'll see the pixel as soon as I add this thing to the ground state. If I add this thing to the ground state, and that's what this picture here is going to be, if I add these two, this one's symmetric, this one's anti-symmetric. Result is a cancellation of the wave on one side. This is negative, that's positive. They're always out of phase. So when I add them, no matter how fast they're wiggling, I'm going to get something here that, if I did it really carefully, would be zero. Right now it's something that's very small, wiggling. Okay? So that's what I'm going to do. I'm going to add the, while I'm here, I'm going to add the ground state back in. Okay? But let's just do it with the thing standing still so that I get time to adjust this thing. So here's the excited guy that's anti-symmetric. And now I'm going to add the pause. I'm going to add the symmetric part with the ground state wave to it. Okay? Now I've got to remember how to do this so that at this moment I completely cancel the wave on one side. And that means I have to make it at right angles to those, the way this thing has been phased. Now I'm going to let it go. You ready? Resume. Well, it starts wiggling, okay? But what you can see is it's starting to build up the thing on the other side. It's sneaking through there, right? And not only that, what's really amazing about this thing is, like the classical coupled oscillators, that one is 90 degrees ahead of this one. The one that's feeding is 90 degrees ahead of the one that's following, or the one that's eating. This one's feeding, that one's eating. That one's blowing, this one's sucking, okay? The idea being 90 degrees is the best you can do for transferring oscillation in a resonant situation, which is what this is. And you see, it's just about to die there, but all the way to his death, he maintains 90 degrees phase ahead, and then he goes out the back door and becomes behind by 90 degrees. And as soon as he becomes behind by 90 degrees, well, then this is the blower and that's the sucker. He's gone from being the blower to the sucker. And this one now is feeding that one, shrinking as he goes, and that one expanding as we go. So this is what tunneling is. Tunneling is just a really slow transition. Same geometry, 90 degrees. The same geometry that causes this thing down here to go back and forth really fast. You can see the 90 degree to a certain extent, but it's over in less than half a period because there's so much open space between them. They really are like Siamese twins now, whereas these are separated, and that's when the tunneling. So when we get to talk about the tunneling of angular momentum in the molecules, we're going to be talking about something that's exponential. As I raise this barrier here, the splitting between the two becomes astronomically small, exponentially small. So right now it's less than a pixel. It gets a millionth of a pixel if I take the thing up, so that you get them e to the sixth, or 10 to the sixth if you convert your units. Okay, so that's what I'm trying to show on these diagrams right here in static. I think you probably see that it really helps to have animations of the things that we've had in our quantum mechanics books since 1905. We're over 100 years into this, and we really need to let our visual systems, our visual brains, get a grasp on what is going on in modern physics. So I thought, you know, we ought to see this. Now, these things we rushed through when we taught this course before. We should not rush things like this. When you get to be a teacher, you don't want to rush this. These are fundamental things that have nothing to do with advanced mathematics, really. It's just, you know, sines and cosines. And they're complex combinations, which is the way we teach relativity. In fact, when we do it, then relativity and quantum mechanics become the same subject. Okay, any questions about this? We've got a little bit more time here to go, but there's some things I really want to show you that are, you know, are spectacular results of this. Yes.
Brett had a question about the algorithm on those. Professor Harter's got it written up in detail, but for the older app. So get together with him, and it's written out really, really great.
Well, in fact, all of this is coming out of QTCA, Quantum Theory for the Computer Age, which is this guy. This handbook here. Okay.
And the chapter that you wanted us to study.
This is Unit 4.
Unit 4. That's on this book, right?
Yeah, Unit 4, which is the fourth one in there.
And online in nice format.
Yeah, this is you know, in real good shape online. I mean, you can't print as precisely as you're getting it online. At 300 dots per inch, you know, you've got a lot more on your screen, right? So, you know, but this is paper, you know.
conversely, we also have this online. I'm going to put it in our
Yes,
site.
that's
so
not
it's
online.
accessible.
I was going to ask.
But that's in scanned format.
Yeah, that's low resolution scan with no
So
color.
you can't select text.
And it has no color, so it doesn't, couldn't do anything about that.
One of the others, but it will be on here in a day or so. It'll be right on the top with the other text. Sorry.
I'd rather buy that book.
Pardon?
I said I'd rather buy that book because like using computer, kind of like I get really tired. My eyes get really tired. So
Yeah.
It's a
I
beautiful.
just the old. I'm just forced at the old style way.
Yeah. Well, the old style way gets your tired eyes too.
Yeah.
Yeah. Okay, let's go ahead here, because if two added waves can do some weird stuff, let's try 100. Or in this case, I'm just going up to 10. Okay? So if you add up 10 cosine waves, they all are equal to 1, so you add up 10 of those guys, and here I've divided by 10, so I get something that's a unit height there. Then I get the sine x over x. Well, to be crude, you get the finger. That's what it's telling you. It's saying, hey, you.
So that's
Take the bird.
so that's basically if I were doing like a two slit experiment, that's what I would get, right? Or something like that, because there is like a wave mixing thing that is happening at the boundaries of those.
That's what we're going to show animation of. Now, you can go. What's really powerful about modern atomic, molecular, and optical physics is that now we can multiplex. We can go backwards. We can make a bunch of pulses and put the pulses back together to make a cosine. That's really impressive to do that. But this is what's been going on for well over 100 years in experimental labs now, is building the combinations of cosines to make pulses. And that was a Nobel Prize in 2005. The frequency combs and the high-speed pulses went along with Ken Evenson and John Hall's work using CW to measure the speed of light to about 100 times more accurately.
What is CW?
It stands for continuous wave, or cosine wave. I make jokes about this. Or colored wave, okay? CW can stand for a lot of different things, but the actual jargon is continuous wave. When they say you have a CW laser, they mean a continuous wave, which is all we usually have, right? You turn on a helium neon or one of these laser pointers, that's a CW. PW is where it's at. That's what gives us the frequency combs. And I mean really fast pulse waves. But this is what I would like to look at quickly. And also while you're at it, just look at what happens if you take the cosine wave, right, which has just one wiggly to it. There's that one peak right there, the one fundamental frequency. Okay, there's your friendly old neighborhood cosine wave. Just put 2 on and already it starts to give you a pulse. Okay, but go to 5 and wow, it's getting pretty impressive, right? So if I've got a delta nu of 5 nu, okay, I can make something like that. But when you get up to about 50, then you really see what it is you're dealing with. You get up to 50 of those guys. I'm way out to 50 now, right? But that's brought my width in to 1 over 50. And that, my friends, is called the Fourier-Heisenberg product. Delta t, delta nu product is 1. the product of time and per time is 1. Nothing mysterious about this, other than the fact that it's mysterious in terms of the wave that's being made, right? So what we're doing here is, as we put more and more in this direction, we're getting more and more particle-like. Pulse wave-like is what you really should say. And these things are pretty much zero in between. Not exactly, but pretty much. So they're much less prone to interfering with other ones like them. They behave like particles. They don't do anything, and then something happens, maybe. Actually, with light, nothing happens. They go right through each other. Okay. So, you know, all of that is really cool, but I'd like to play with these pulses just a little bit more here in a situation where we've got some dispersion. Okay? So that's what we're doing here. Making these concepts as clear as we possibly can. And now, we're going to take prisoner M, who is kind of, you know, he just eats cheeseburgers every day, so he's kind of fat, right? Prisoner M starts out, he takes up the whole cell, right? We're going to trim him down. Okay? We trim him down until he's only 1/100th as fat as he was. Okay? That's what's going on here. I'm making a delta function at the position A. That means, if you know your Dirac notation, that you sum over a lot of energy states. Now I don't make it to infinity. I had to stop. I just got tired. Couldn't make it. But in your textbook, they take this to infinity, right? And that makes you what's called a Dirac Delta, okay, which would have infinite height and 0 width. Okay? Well, we're going to actually do this on a computer, so you can't do that. But it's also instructive to see what we really get here, because we get a lot of wiggles here. We have to look at those too. How big are the wiggles in width and height? Okay? So this really boils down to this coefficient A times a sine wave. That's what's going on here. Is I'm summing over all the ends of sines here with this coefficient A n. And that's making this thing. I call it the ultra-thin prisoner M. This is again back to chapter 12, unit 4. Okay, 100 energy states. Now think what that means. 100. Okay, 100 squared is 10 to the 4th. So how high up the ladder in the infinite prison well did I have to go to get the energy of the highest state to make this guy so thin? I told you I had to work out hard. He has to work out really hard in order to get that thin. Okay? 10 to the 4th. If he's a meter higher, we're 10 to the 4th meters. It's really high. It's like a mountain, right? The top level of this thing is like a Mount Everest, right? That's how high you have to go to get this. You have created a bomb. This is a bomb. Because all that energy can come out. Now every quantum mechanics textbook goes and starts off with, oh, we got a wave packet here and it gets wider. Big deal. This is a bomb. This is what you should show. We've got a computer here, we can do it, right? Now, I don't have that one programmed right away, but let's just look at what would look like if I did that. First of all, here's the numericals of the thing, where I am going to turn this sum into an integral so that I can actually make some statement about what's in this region right here. So I go ahead and just write this thing out, this wave function out in some detail. And so what I get is a thing that looks like this. Okay. There's the result. So what you see when you look at that thing is a sine x over x minus a, okay, and this thing is only big and then near the value of A. This is x plus A. So this is really small here. This term is really big. This thing is you know, like 1. Okay, this is Mount Everest right here. So I'm just going to get rid of that. Okay, for x very close to A, that's the only one that you see here. And the result that you see from this is what I call the last in, first out effect. And that's, you know, computer jargon, right? You put a bunch of stuff in a stack of memory, right? Last in is the first thing you pull out, because you pull it out at the bottom, right? So what this is telling you is the last K max value that I stopped at, and I stopped at 100 here, the last K max value dominates. All of the other K gets smothered by interference with their neighbors. So that's what's so weird about always adding up and then dropping it and cutting it off. This is the boxcar spectrum that we're using to make this thing. And you end up with hair on the sides, but the hair all is of the 100th wave number. Okay, so that's one lesson to learn that's, you know, you can state clearly. It's an approximate statement because I dropped off this other term, but that term is very small percentage of Mount Everest. Okay, so that's what we're going to let blow up, and that's what it looks like when it blows up. Now look at the timing here. This is the period of the very lowest transition that we've been working with. And this is 0.04, this is 0.0008, 0.001 here we're talking about 0.2, okay. Right about here at 0.0020, this thing gets to the other side. And there's the link up, by the way, if you want to read about this thing in particular detail, okay. So this is already a little late. This thing's already exploded. It's detonated, okay. This thing is detonated across the thing. And last out, last in, first out. All the wiggly stuff is down here now. It just blows down the end there. And you can calculate that very nicely. I'll skip over the details here. Get the classical value from the group velocity, and then figure out, you know, where it takes. You calculate for n equal 100 in order to get one-way time for this thing is 0.0025, and that's pretty close to this. And there's a line that sort of goes through the head of this thing, and at exactly 2.5, it hits the wall. Remember, it's an infinite prism, so none of this wave function goes into the wall, even though it looks like it does. We're talking about 100 waves, 100 K value waves here. Okay? So there's just something that's just spectacular because of the numbers involved. This was a bomb. This is a bomb, and it's going to go crazy back and forth. But it never loses its memory of where it was. This is at 1 tau 1. This is what happens at 1.5 tau. Prisoner M reforms, unexplodes, but is upside down.
What makes it pick up a PHYS, Dr. Harter?
In order to answer this, we have to go to the Bohr rotor. The square wall is it's really hard to deal with. After you see the Bohr rotor make the combination that I showed in the very beginning, you can explain this. But let's do the Bohr rotor. Okay, now I'm going to do that in slow motion. Okay, the question is where to do it. By the way, this is what happens if you wait a third of a period, a fifth of a period, a seventh of a period. You get little images of the sine x over x wave.
What happens?
Where magnitude is red, real is blue, and cyan is the imaginary part. They're all in there. We're going to see that in the actual animations we'll do.
What if you have like tau over 1,000?
Well, that's what we were looking at. And that's
Like
the
a
amount
bow.
of time it takes to get halfway, the blast wave, the front, halfway of a thousandth, right? It took 2 to get all the way to the end, 0.025, right? 2 thousandths and a half to get to the end. Is that right? Let's go back here. Here, 0.002. Yeah, and according to the calculations, we're almost there for the main part of the wave. Does that answer what you were asking?
Yeah.
Yeah.
So, Dr. before you go to the rotor, one quick question. So, will the width of the well decide how many times the wave function can collapse? How many times you can observe collapse and revival? Is it determined by the width of the well? How wide the well is?
No, it's really more, well, in a sense it is, because tau 1 is determined by the width of the well.
That's right.
So
Right.
this thing will kill itself
Because
if you wait long
frequency-
enough, right?
Yes.
It just will die out.
Because tau 1 is related
No,
to the
it's not.
frequency.
This is perfect quantum mechanics here.
No loss.
So those phasors, are all related to each other as though they were part of a harmonic oscillator spectrum. So at some point they all line back up again.
That's the revival.
That's the primal revival.
But how,
And that's what we'll see in a
how
minute.
come something like this, after if you have waited long enough, that just
You-
died
you
out,
only
will
waited-
come to...
Yeah, you only waited a fraction of the period. You get that fraction flipped over number of pulses. We're going to see that in a minute. We're going to see that in a more reasonable way.
Now your waveform doesn't ever go to 0
There's
identically.
this-
Yeah,
so-
that's true.
It's
Okay,
identically
so
the
Yeah,
same.
whenever
that
the-
answers my question. So that tiny wiggling that you're left it is just enough to revive an entire wave.
And
Or
both,
waves.
remember, the real and imaginary parts are always part of this, right? Always part of it. There's always, these are oscillators, and the 2 variables are the position, that's the height of the wave, and the speed that height is moving, that's the imaginary part. So you've got to get yourself into phase space to understand oscillator behavior. And all of waves are oscillator behavior. That is really an important point to keep in mind while we do this stuff.
It shows the power of complexification.
So what I'm going to do now is a gently localized rotor wave. I'm going to give it a Gaussian distribution of a lot of frequencies, or maybe just a few frequencies. With just 2 frequencies, plus and minus, I get the standard beats that we were seeing over there. That's just a transition. I go from this side to this side. This is wraparound. These animations that we're going to be doing are Bohr rotors, so they get to wrap around like this. This is what we're going to see when we run the animation for a very gentle pulse. And we'll see the gentle pulse actually graphed out when we run this, hopefully. Always should be humble. But what you're going to see is little traces magnified many times. This is a quantum fractal. It used to be said that quantum mechanics can't make fractals because quantum mechanics is all just a bunch of oscillators. But if you got lots of oscillators, you can get pretty close. As close as you want. Just depends on what kind of distribution you're willing to pay for.
So can you go to the previous
This is
slide, please?
Animation.
Can you go to the previous slide? So what is this cylindrical image on the right?
Well, it's this
Time evolution.
page here. This is going here in units of 2 pi,
Yeah.
okay? From pi to minus pi,
Okay, yeah.
right? So this and this are the same point,
Right.
and that's what I get to do.
Oh, okay, you just wrapped it.
It's a wraparound, right? So we go from 0 to pi if you want, or else we go, plus pi over 2 to minus pi over 2. Yeah. So that's the wraparound coordinate for this. Yeah. This is Bohr rotor, so I get to do this. I can't do that with just infinite prism. But the infinite prism is half a Bohr rotor, so you get, you know, similar behavior. Okay?
And are those bright spots the peaks, the brighter spots that you have on the...
Good that you ask. When you're dealing with waves, you don't look at the peaks. You look at the zeros. As in the Sherlock Holmes thing, as everyone quotes, it's where the dogs didn't bark that the mystery is solved. Okay, so you say, no, I'm used to dogs. I look where they are and I don't need them barking. Okay, okay, if you want to trace the particles that come out of here, there's a nice particle path right there, that dark thing. And then there's another one, you might be able, if you ride really hard, you might be able to see the one that goes this way. But it's really hard to see, and there are a whole bunch of them here that you just don't get to see. But the zeros, they show up.
Show the animation. It'll be really, really clear because they'll just trace out before
Yeah,
you see where
it's
the
a
wave is.
very nice, slow animation. I go ahead and run it on that one.
Either or.
I think we can get away with that one. Now the trouble with this screen is that it doesn't show this picture very well, so let's go ahead and make use of it where it is strong. Okay, so I think I can get started just with this link. Famous last words, right?
I actually swapped that out.
Okay, pulse right there, pulse all across the bottom there. And now it's wrinkling at the bottom because it ran into itself on the bottom there. But here's what we're tracing. We're tracing those things very carefully. And everywhere I get a set of zeros all the way across, like right now, that's 1/8 of the revival period. That's 1/7 right there. Here, I'm seeing 1/6, and I made a 3-shaped thing. Whenever it's an even number, you have a factor of 2. There's 1/5 with 5 full thing. Here comes, that's 2 9ths now. Here comes 1/4. I get 2 things, north and south pole. And that's a great big, a quasi-revival, fractional revival, 1/4 fractional revival.
So the bright line is not, right?
The white line, I would call it a 0, but node is a good, usually when you say node you mean a standing wave and it stays right there. These don't stay, right? They come and go.
Okay, so the white line is...
Where it's not, where it's not.
It's instead of all the zeros...
Okay, here you go. Look at that. The pulse is reformed in the South Pole. We're at halftime. This is halftime. Now it's just going to unwind like this if I let it keep going.
So the particle goes through the white line.
No,
No.
no, no.
Well, pause it.
If you asked for a particle at any of those points, if you had a little thing there that was a detector, you get 0.
It was never there.
That's where the particle's wave, which is its life blood, its phasor, is canceling completely.
So
Completely.
Self-interference.
Yes. Yes.
So can you but that doesn't seem intuitive. Like how can you interfere with yourself when you're like, if I were a particle, why would I interfere with myself?
It's topology.
Because
It's
in space and
one-dimensional
time,
sorting.
those waves are still there. The real and imaginary parts are still there. They just have to be canceling right there.
Because of the out of phase thing.
But they're alive. It's alive. It's alive everywhere on the screen. Now, let's, we have a little bit of time. Let's do a slightly different thing here. First of all, what I want to do is make sure I show the Fourier bars. Okay, I didn't show those. But this time I want to do the boxcar. Okay? And while we're at it, let's do it on this screen too, but I'll redo the one that we just did. That's asking a lot. I've got to get it going first of all. So there you see it at the North Pole. Now I'm going to go to local control here. I'm going to go down here. I'm going to ask for the M bars, but I'm not going to put a boxcar on. Okay? So let's go back here, and I'm going to launch this one.
What's a boxcar just want to?
Remember when I said that if you had a distribution that was, you know, the same, and then nothing,
Oh, right. Yeah.
makes a boxcar.
Oh, okay.
That's like CW. It's a jargon.
Okay.
Boxcar. We got a boxcar integrator here, right?
Okay.
Okay. They always talk, you know, real tough. The laser jocks. You gotta watch out for them. Okay, so I'm going to launch this one at the same time, and I've got to play here. I'm just going to see which one of these
Who's fastest?
goes faster, just out of curiosity.
You want me to?
Do you want to come up and do it?
You just do us. We'll go on no.
I'll start at 3. Oh no!
Well, we can restart it. Let's just
Yeah.
get together here and restart it all at
Yeah.
once. I'm gonna launch mine first, and then I'll restart it. Just tell me when I ought to
Okay,
get the.
go ahead.
Here he goes. Now we go. It's restarting.
Ready. Okay, this is one that got the boxcar, right? Look, it's crazy. It's absolutely crazy. Whereas this one, so far, it hasn't really made any zeros. It's got a few of them showing up here, and only about now am I getting some zeros, right? You can see by the line, it's just barely getting close to 0. Then I got 13. There were 13 peaks on the thing. But this one, all the peaks have hair on them. You see? Look at that. See the hair on that? It's a sine x over x. So you get all this crazy stuff for the zeros. This is fractal. And this one's going a lot faster than this one. I guess that's because this computer isn't as fast as that one as far as...
It could be. You want to
Yeah.
close all your windows and other apps down to
That's
put it on
true.
equal footing.
Yeah. It's,
Probably still hold up.
this is a newer power book than that one. That one's a couple of years old.
This
But anyway,
one's
look at
driving
the
millions of
amazing
pixels.
structure of that.
Right.
There's halftime. Now it's just going to do it in reverse.
So it just comes back.
Yep. Then the pulse will really reform up here.
That's the revival.
If we let it go. If we let it go all the way up,
Yeah.
up to there.
Yeah, by
Right.
definition. Now everybody gets together again.
Yep.
So, Dr. Harter, I have a question. So, if in this case, in a rotor, you should observe periodic collapse and revival indefinitely, right? Because unlike infinite square well, which
Yeah,
is
there's no
constrained.
losses. No, none of the stuff you have to worry about on your thesis. No losses. Right? That's the main pain, right? Is trying to get rid of the losses, right? Here, we don't have any friction here at all. No absorption, no fun of that kind of stuff, right? That bothers experimentalists so much. Well, we are getting the time. I want to show you one more thing, real quick here.
It's super neat having them side by side.
These are all things that you can read about.